thank you very much for inviting me. It's a great pleasure to be here. And I will report about a topic that I've been working on for the last maybe 4 years. And this will be a summary of results, and there won't be a lot of proofs, but if you want me to talk about details, please stop me and ask questions. Okay, so let's see if there are simple definitions of complicated sets. Okay, so sometimes people call objects that can only be constructed using the axiom of choice pathological. I'm not really sure if I like this name, but I will just because I need some name for these objects. And let's see some examples. So examples are non-Lebesgue measurable sets of reals, Q bases of the real numbers, then well orderings of power sets of infinite cardinals, bistationary subsets of uncountable regular cardinals, so stationary and co-stationary subsets, and colorings witnessing failures of weak compactness at, say, accessible cardinals. So in all of these cases, you actually need the axiom of choice to construct these things, because they are...
I might complain about bistationary because you have different cardinalities.
Yeah, but for omega 1.
Oh, for omega 1?
Yeah, I mean... so there are models where the club filter is an ultra filter.
Yes.
Yeah.
Within the same cardinality. Within the same cardinality.
Okay. Okay, so and now the natural question is whether there's some way or some property that allows you to distinguish between these sets and sets that are constructed in some explicit way. And I think this is an interesting question because I think it tells you something about the set theoretic universe you're living in. I mean, what I'm going to talk about is that definability is a way to distinguish these sets from explicitly constructed sets. And so as a motivation, there are very many results in descriptive set theory that say that such pathological sets cannot be simply definable in second order arithmetics. So, for example, sets defined by sigma 1,1 formulas are Lebesgue measurable, so these pathological sets cannot be simply definable, and same for well orderings and so on. And moreover, we have that canonical and strong extensions of ZFV allow us to extend this implication to arbitrary definitions. So if we have large cardinals or forcing axioms, then such pathological sets are not definable at all in second order arithmetics. Okay, and I want to do in this talk is I want to consider the set theoretic version of this question. So I ask whether such sets can be definable in V by simple formulas. And my main examples will be well ordering of the reals and bistationary subsets. Okay, and now I have to say something about what simple definitions are. And first of all, I mean, I think there are some variations how to do this. And so we have to say something about what kind of parameters we allow. And to avoid trivialities, I just want to use cardinals and sets of small hereditary cardinality as parameters. So, I mean, if you want to check whether you have a definable bistationary set, you don't want to allow the set itself as a parameter. So, so there it's kind of natural to only allow the cardinal you're looking at and sets of smaller cardinality as a parameter. Okay, and to talk about simple formulas, I use the standard approach and look at the Levy hierarchy. And just as a quick reminder, so we use a language with just the epsilon symbol, and then we say some formula is a sigma zero formula. If it's contained in the smallest collection of formulas, it contains all the atomic formulas, and it's closed under negations, conjunctions, and bounded quantification. And then we step up by saying that something is sigma n plus 1 if we add one existential quantifier and then a negated sigma n formula. And it's not too hard to see that the class of formulas that are ZFC provably equivalent to a sigma n plus 1 formula, this is closed under existential quantification, both types of bounded quantifications, conjunctions and disjunctions. Okay. And now, first observation is that when we look at this kind of definability, then the only interesting cases are the cases of sigma 0, sigma 1, and sigma 2 formulas. And this is because of the following proposition, and this is really just a complicated way of saying that the well ordering of hot is a good sigma 2 well ordering. So what this means is that you have this well ordering of hot, and the class of initial segments of this well ordering is defined by a sigma 2 formula. And now what we can do with this is that, so we look at some type of objects, so consisting of sets of ordinals. Think about this as like the canonical codes for well ordering of the reals coded as sets of ordinals. And if this class is delta n definable, so both the class and its complement are sigma n definable with some parameter, then if this class contains something that's in hot of z, then there is such a thing where I can define the singleton in a sigma n way. Okay, so what does this mean? So take n as 2, then well orderings of the reals are sigma 2 definable in this way, and bistationary sets too. So if there's an object that's in this class that's definable in some way, then there's a sigma 2 definable object. Okay, so this is why we can stop at 2. Okay, so the interesting cases are 0, 1, and 2. But then, okay, so what this also tells us is that if V is hot, then we can define all of these pathological sets in a sigma 2 way. So somehow sigma 2 is not simple because in hot you can just define everything in a sigma 2 way. And all of the extensions of ZFC that we will consider are compatible with the assumption that V is hot. Okay, so sigma 2 is not simple, but in some sense sigma 0 is too simple, because it's, in all cases, you can run some standard argument to show that you cannot define the set in the sigma 2 way if you allow just simple parameters. So the interesting case is sigma 1. Okay, so this will be our class of simple definitions.
A naive question. So is the assumption that V equals hot, or that hot is large, is this a natural assumption?
It's at least compatible with...
Well, V equals L is...
Yeah, but it's compatible with all large cardinal axioms and with forcing axioms.
Okay, so we're saying, well, inner models have this property, right? The canonical inner models have this property usually.
Yeah.
So, but forcing extensions typically don't have this property.
It depends, but basically all natural axioms are compatible with this. So PFA or MM or...
So it's just global choice. It just says you can define it in all the sets.
Yeah.
To be able to start set.
Yeah. So
natural, but it's not provable.
Yeah. But at least the extension of ZFC that I will consider are compatible with this, so they cannot rule out the existence of such definable sets. So I just want to use this to argue that sigma 1 is really the interesting case.
I think there's a term that says you start with any model that there's a class forcing extension such that the ground model is hot of that.
Yeah, but the problem is that the hot does not know that it's hot. So
That's the heart of the heart.
yeah, but I think the standard way is you code V into the continuum function, and then V knows that it's hot. So you get a global well ordering. This is all you need. Okay, but so we will focus on sigma 1, but I will also say something about sigma 2 in some cases. Okay, and I will start we're talking about well-orderings of the reals. And here, I first want to consider sigma-1 formulas that only use reals as parameters. And there we have some classical results that completely tell us what's going on. And the first observation is that we have the following characterization of such sets of reals. So some set of real is sigma-1 definable with parameters in h omega 1 if and only if it's sigma-1, 2 as a set of reals. So I think that's it's not too hard to show this. It's somewhere in the X book, but you can also come up with a proof rather easily. Okay, but now we can take this and combine it with some classical result of Mansfield and just rephrase Mansfield's result in the following way. So the following statements are equivalent. So first of all, there's a well-ordering of the reals that's sigma-1 definable with elements of h omega 1 as parameters, and then that's equivalent to the statement that the reals are contained in L of x for some real x. Okay, so this completely describes the situation for sigma-1 with parameters in h omega 1. And this has a, so if we have sharps for reals, then no well-ordering is definable in this way. So sigma-1 with parameters in h omega 1. So large cardinals rule out the situation. Okay, but now we want to consider larger parameter classes. And what we get is such a characterization for the next level of the projective hierarchy. And this is in a paper I wrote with Ralf Schindler and Philipp Schlicht. And so we need some strong assumption, and you can pick one. First of all, if one assumes that there's a measurable cardinal above a wooden cardinal, or you assume that bounded Martin's maximum holds and the non-stationary ideal on omega 1 is precipitous. So in particular, Martin's maximum implies this second assumption. Or you assume that there's a precipitous ideal on omega 1 and a measurable cardinal. So if one of these assumptions hold, then we can characterize sigma-1 3 sets in the following way, that they are just definable sets of reals that are definable by sigma-1 formulas with parameters in h omega 1 and omega 1. So we added the cardinal there as a parameter. And if you do this, you get go up one level in the projective hierarchy. Okay, I will show you a sketch of the proof of this result. Okay, and later on I will argue that you need to assume something here. So this is not a ZFC characterization. Okay, so let's, yeah.
What do you mean by go up one level in the projective hierarchy? Is this only in this, this is in this scenario with the forcing axis, or do you mean?
Yeah, I mean, so if you remove omega 1 here, then you get sigma-1, 2 in ZFC.
I see.
But in this, under these assumptions, or under one of these assumptions, you get sigma-1, 3. And
well, one direction is ZFC.
Yeah. Yeah, so this is ZFC.
Yeah.
And actually, and this will actually be relevant later on, this direction is provable in ZFC for any kappa. So if you have h omega 1 and kappa here. So this is Schoenfield absoluteness, right? So, because you just need some uncountable parameter. Okay, so let's sketch the proof. So we assume that either the first or the second assumption hold, and the case for precipitous ideal plus measurable cardinal, this is very similar. So we fix some sigma-1 formula and some parameter from h omega 1, and we look at the set that's defined by the sigma-1 formula, this parameter z and omega 1, call it x. And now we define y to be set of all reals with the following property. So we say that there is a countable transitive model of ZFC minus, and this model contains some delta, and it contains the relevant real and this parameter z. And this delta is a wooden cardinal in there, and the model is omega 1 iterable with respect to the countable stationary tower forcing and its images. So you do some forcing to get an elementary embedding, and the assumption is that you can iterate this up to omega 1. which is the same as saying you can do it for all countable ordinals. And this formula holds in the model with its omega-1. Okay, and if you stare at the definition of y for a while, then you will see that this is a sigma 1,3 definition. And this is, so the first existential quantifier is there's a model, and then iterability is pi 1,2.
You want the parameter z also, the same. Z is fixed, right?
Yeah, so this should be bold-faced here.
No, I mean, you say phi, it has only 2 parameters.
Ah, sorry, yeah. The z is, yeah. Yeah, sorry. But the y and the other parameter, they are not moved by the iteration. So they're just, okay, I will say a few more words about this, but, okay, but, so this is sigma 1,3. Because iterability, you can phrase it in a way that's saying for all countable ordinals, it's iterable up to this length. And that's pi 1,2.
I mean, that's not equivalent to omega 1.
For, I guess for generic, I think you have to prove it, but I think in this setting, I guess it is.
We can talk about that.
Yeah.
I mean, what you're saying is definitely true if you replace omega 1 by pi 1,2. I think the rest is
Okay. Yeah, I think we proved it. Okay, but then.
What do you mean by omega interval respect to the stationary tower?
I think in each step you force with the countable stationary tower forcing, and in the later successor cases you force with the image under the previous embeddings.
Oh, Evans mounts FC minus. Okay, you add ordinals when you take the. Wait, when you force with the stationary tower, you don't add ordinals. You just fatten the model, right?
Yeah, but you iterate it up to omega 1, so you will add. You start with a countable model and you iterate it omega 1 many times.
So when do you increase the height of the model?
Limit, at least in limit stages.
Oh, I see what you do.
I mean, it takes some lemmas to prove this. Yeah. Okay, so now what I claim is that this set y is actually equal to x. Okay, so just a quick overview how to prove this. So, so if you have an element of x, then this statement holds. So this is a sigma 1 statement, and the parameters have size at most aleph 1. So you can also code the witness for the existential statement into a set of size omega 1. So you can code the truth of the statement into some subset of omega 1. And now both of these assumptions imply that M1 sharp exists for every subset of omega 1. So you get this model for the subset that codes the truth of the sigma 1 statement. And if you take a countable submodel of this, then it will witness this statement. So that's one direction. This shows that x is a subset of y. And in the other direction, if you have such an element of y, then you can iterate this model up to a model of size omega 1. And then this statement here with the z added will hold for the real omega 1. Okay, but it's a sigma 1 statement, so it's upwards absolute. So it will hold in V. So the element y will be an element of x. So that's this trick that I will use several times today, that I take some big model, I take a small submodel, and I iterate it up again, and then I use sigma 1 upwards absoluteness to say, okay, then this formula really holds for the corresponding parameters.
You use the woodenness just for the well-foundedness, or just for the iterability? Is that it?
I think for the iterability, you also use the sharp above.
The sharp above the.
Yeah, There's actually quite a lot of things you have to prove to prove this iterability.
But you need to put this account of the stationary tower.
Yep. Yeah.
You can't just force with P omega 1 mod NS, and it's just the generic iteration.
I think you also need the sharp to see that you can go on until up to omega 1.
I mean, are you going to tell us that you really need this
Yeah.
one here? Okay.
Yeah.
I was thinking maybe you could do it with less, but you're saying that.
I mean, I will present a result where I show that you cannot do it with the wooden alone.
Yeah. Okay. Well, that
So,
answers my
yeah.
question.
Okay, so let's see, maybe it's already, no, it's not on the next slide, but okay, so this has an immediate consequence. So if we assume one of these three statements, then no well ordering of the reals is definable in this way. So by a sigma 1 formula with omega 1 as a parameter and elements of h omega 1 as parameters. And the reason
The hypothesis was really just that M1 sharp exists over every real,
over every subset of omega 1.
or a subset of M1.
Yeah.
That's what these things imply.
Yeah, so I mean, so the first result tells us that such a well ordering would be a sigma 1,3 well ordering, and then all of these assumptions give us enough regularity properties to say that a well ordering cannot be definable in this way under these assumptions. Okay, so large cardinals in particular rule out the existence of such definable well orderings. Okay, but now we also have a result that shows that this large cardinal assumption is close to optimal, and it also shows that this characterization of sigma 1,3 sets cannot be derived from something substantially weaker. In M1, the canonical well ordering of this model is definable in this way. So it's a sigma 1 with parameter omega 1. And also the set singleton of the reals, this is also definable by a sigma 1 formula with parameter omega 1. So in particular, this tells us that some universal sigma 1,3 formula or pi 1,3 formula is also definable in this sigma 1 way. Because if we have the reals as a parameter, we can define all kinds of projective sets in with a sigma 1 formula with parameter omega 1. So you really need the measurable above the Woodin cardinal to get this characterization and to get the non-existence of well orderings.
And you can that object is sigma 1. Is that what you're saying? No, you say the HC of M1.
Yeah.
If you have omega 1, you can actually cut out the M1 hierarchy up to that level.
Yeah, I guess what the proof shows is that you can define the collection of mice in a sigma 1 way, and then you can define the well ordering in this way.
So we take the omega projected the mice.
Yeah, something like that. Okay, so so this results are optimal in a certain sense, and what we also did is that you can increase the parameter set to universally bare sets. So if under stronger large cardinal assumption, so if you have a proper class of Woodin cardinals, then you can allow universally bare sets and the non-stationary ideal as parameters, as extra parameters, or as predicates in your sigma 1 definition. So this means that you have this set and its complement as an atomic formula in your language, and then you define sigma 1 formulas in the corresponding way. Okay, and this is basically the same proof, just with a stronger machinery. Okay, but what we can also do is that we can replace these generic iterations by real iterations of small models and get results for sigma 1 definition that use large cardinals as parameters. And for this we need the following notion. So First of all, I want to say what a weak kappa model is. So it's just a transitive model of ZF minus, ZFC minus of size kappa that contains kappa. And then Philip Welch and I think his name is Ian Sharp, they defined the notion of omega-1 iterable cardinals. So this is just a cardinal with the property that whenever you take a subset of kappa, then it's contained in some weak kappa model, and there's a filter for this model such that the resulting structure is iterable. So this is somewhere in between sharps and the measurable. Okay, and if you have this, you can, as I said, run this argument for the large cardinal as a parameter by taking real iteration instead of generic iteration. So let's see. So if we have a cardinal that's either omega-1 iterable itself or it's a stationary limit of omega-1 iterable cardinals, then we get the following characterization of sigma 1,3 sets of reals. So something is sigma 1,3 if and only if it's sigma 1 definable with parameters the large cardinal and elements of h omega 1. And the proof is really the same proof as earlier on. So we fix such a cardinal, we take a formula that defines a set of reals in the sigma 1 way. And now Y is a collection of all reals with the property that there's some countable transitive model of ZF minus containing the relevant sets, and some cardinal in this collection such that the sigma 1 statement holds in M, and there's some external filter such that the structure is iterable. And then again, it's you can show that this is sigma 1,3 because again, iterability just means countably iterable for all countable ordinals. And this set Y is the same as the initial set X. And okay, so how do you prove this? If you take an element of X, this formula holds. So again, you can, the parameters of this formula, they have size at most kappa. And it's a sigma 1 statement, so you can capture the witness in, or code the truth of the statement in a subset of kappa. So you find a model of size kappa, this is a model of ZFC minus, and this sigma 1 statement holds in there. And now our assumption, if we are omega 1 iterable, then we get this external filter. And in the other case, if we are stationary limit, then we just have to run some elementary chain model, elementary chain argument where we build a chain of smaller models, and then the stationarity of the omega 1 iterable cardinals give us some smaller cardinal where we have the external filter for the corresponding model. Okay, and once we have this, we take a countable elementary submodel of the model we construct, and now this will also be iterable. And so you get a witness that the set we started with is in Y. And in the other direction, if you have an element of Y, then you take this model and you iterate it up to kappa because it's fully iterable. And then the sigma 1 statement holds in the kappa's model, but you're sigma 1, so you're upwards absolute, so it holds in V, and you're an element of X.
Can you show us the hypothesis again? It's about the iterable, omega 1 iterable recap. So somehow you're saying there's a wing cardinal in strength here?
No.
But earlier you said if you don't have more than a wing, you can...
Yeah, but you have this kappa as a parameter.
How big is kappa?
Kappa is a large cardinal.
Oh, that's the point. Oh. So it's a better parameter than...
Yeah. Okay, so but now if we have this, we can get some easy corollaries out of this, and this is because measurable cardinals are omega-1 iterable, and wooden cardinals are therefore stationary limits of omega-1 iterable cardinals. So what we get, for example, is that if kappa is either a measurable cardinal above a wooden cardinal or a wooden cardinal below a measurable cardinal, then no well-ordering of the reals is definable in the sigma one way with reals and this cardinal as a parameter. And this is just because this result about iteral cardinals says that, okay, such a well-ordering would be sigma 1, 3. And then since the cardinal is actually much larger, there are no sigma 1, 3 well-orderings. Okay, so for certain large cardinals, well-orderings are also not sigma 1 definable using these cardinals as parameters. Okay, but now we had omega-1 and we had large cardinals as a parameter, but the interesting thing is that things are completely different for omega-2 as a parameter. And this is somehow, I mean, this was actually kind of already known, but I think for me it was very interesting to see this. And it turns out that well-orderings of the reals that are sigma 1 definable with parameter omega-2, they are compatible with all large cardinals. And the reason is the following. So if BPFA holds, then we have something that's kind of a property that you would expect like in L-like models to hold, namely the singleton H omega-2 is sigma 1 definable with omega-2 as a parameter. So in L, you have that the initial segments of L are just sigma 1 definable by their height. But in models of forcing axioms, this is also true for omega-2. And this is a direct...
Sorry, it's obviously always pi 1 definable, or?
Yeah.
With conjugate.
Okay, and this follows from techniques developed by Casedo and Velichkovich. And these results give us some finite fragment of ZFC minus plus BPFA plus omega-2 exists with the property that BPFA proves that whenever you have a transitive model of this fragment F and it computes omega-2 correctly, then it contains all of the reals. And this is some coding they developed where they, let's see, so I think they coded subsets of omega-1 by reals and reals by ordinals, and somehow everything is mutually coded. And you can express this in a first order way, and all you need to know to decode all the reals is the real omega-2. And I mean, once you see this, you directly see this, right? Because you just have to say that there is some model of this fragment F that computes omega-2 correctly, and you are allowed to use omega-2 as a parameter. So you get this sigma 1 definition of singleton H omega-2. Okay, but you can now use this for the following observation. So if BPFA holds, and there is some well-ordering of the reals that's definable in H omega-2, also there's a bracket missing, by formula of some complexity, but it uses a fixed parameter Z, and that will be the empty set in the interesting case. Then this well-ordering is actually definable in V by a sigma 1 formula that only uses omega-2 and Z. So you have definable well-ordering of an arbitrary complexity in H omega-2, and this will now be sigma 1 in V. But now we can use results of Aspero and Larsen that tell us that we can force such a definable well-ordering that uses no parameters at all together with strong forcing axioms, and we can force this by set-size forcing. So for example, David showed that starting from a supercompact cardinal, we can force PFA double plus 2 holds, and there's such a well-ordering, so a completely light phase well-ordering of the reals that's definable over H omega-2. So in this model, you will have a well-ordering of the reals that's definable by a sigma 1 formula with parameter omega 2 in V. And if you assume large cardinals above this super compact cardinals, then they will stay large in the forcing extension. So such a well-ordering is compatible with all kinds of large cardinals. And you can also get the same thing with MM plus omega. This is the result of Larsen. Okay, so somehow large cardinals do not rule out the existence of a sigma 1 omega 2 definable well-ordering of the reals. And I think that's quite interesting. So somehow omega 2 is in some sense completely different from omega 1 and large cardinals in this sense. But this is because you have more room to code. Yeah.
Uses clubs in omega 1.
Yeah.
How much does it have to do with omega 2 other than some other non-large? I have no like omega 3.
I mean, you also get the sigma 1 definition from all aleph n's, because you can define omega 2 from omega n plus 2.
Oh,
but actually, what I do not know, and this will be one of my questions, what about aleph omega? But more on this later. Okay. Yeah. But I think the idea is that you have more room to code with omega 2. Okay. So now let's look at the other type of pathological set that I want to consider. So here I want to talk about bistationary sets. And I want to study these sets focusing on the following properties. So I fix some n, and I say that some uncountable regular cardinal has a sigma n club property if basically there are no bistationary sets that are sigma n definable. So what I'm saying is that whenever I take a subset of kappa and the singleton is definable by a sigma 1 formula with parameters in h kappa and also kappa as a parameter, then this set either contains a club or is disjoint from a club. So in some sense, the club filter is an ultra filter with respect to sigma n definable subsets. And it actually requires some arguments to show that every uncountable regular cardinal has the sigma 0 club property. So at first I thought it's completely trivial, but you actually have to prove some some lemmas to get this. But this is not really interesting, but it's true. Okay, so this is ZFC. Yeah. But now what's more interesting is that for the higher ends, this property is actually equivalent to a partition property for definable coloring. So I get the following. So some cardinal has a sigma n club property if and only if whenever I take a coloring of the finite subsets of kappa with less than kappa many colors, and the coloring is definable by a sigma n formula with parameters in h kappa and kappa itself, then this coloring has a homogeneous set that's club. So this is a very strong partition property. I mean, nothing you will get for arbitrary colorings, right? So you won't get homogeneous sets that are club, even if the cardinal itself is a large cardinal.
What do you mean homogeneous? You can just take the size of
So for each n.
For each n?
Yeah.
You mean
For each n, you will have the same color of the finite, the subsets of this cardinality. Okay, I will not prove this, but I mean, this implication is easy, and the other one is by induction. And what you heavily use is that you stay within your complexity because the colors are uniquely determined here because the intersection of clubs is again club. So you can have at most one club where you're homogeneous. Okay, and this allows you to stay in the same complexity class with the formulas. And what this also allows you is to just prove this statement here for for the individual finite arities, because you can just intersect clubs to get a big homogeneous set for the collection of all finite subsets. Okay, but this will be very useful later on. But to motivate this, we can use the techniques developed in this proofs about well-orderings to get something about this property at omega 1. So now we have an even longer list of assumptions, and I guess quite a lot of people think that one of these statements is true. So I now added Woodin's axiom star to the list. Okay, and if one of these statements hold, then omega 1 has a sigma 1 club property. So in some sense, these assumptions imply that omega 1 is a Ramsey cardinal with respect to sigma 1 definable colorings. Okay, so how can we prove this? So I will start with the argument for the axiom star. So just as a reminder, so star states that AD holds in L of R, and the power set of omega 1 is contained in the P-max generic extension of L of R. It's not necessary to know what this is. All you need to know, it's some forcing you can define in L of R, and it's sigma closed and homogeneous. This is all you need to know. And then it's not too hard to show that if we are in such a P-max generic extension, then we have this club property for all n's, so we have it for sigma 2. And the reason is just if you assume you have a bistationary set where the singleton is definable in some way, and the parameters are just ordinals and reals, then the fact that the forcing is homogeneous tells us that the set is an element of L of R. Okay, but now in AD implies that the club filter on omega 1 is an ultra filter. So either the set contains a club or the complement contains a club. And this is the whole argument for this proposition. Okay, now to get the first statement. So let's assume that star holds. And I want to now show that star implies that omega 1 has the sigma 1 club property. So let's fix such a generic filter. And we now take a subset of omega 1 where the singleton is sigma 1 definable using parameter omega 1 and some element z of h omega 1. Then, since h omega 2 is a subset of this generic extension of L of R, the same definition defines A in the generic extension of L of R. But now we have this proposition, and this tells us that in L of R of G, omega 1 even has a sigma 2 club property, so then we get the club that either contained in A or in the complement of A. Okay, and this shows that just star implies the sigma 1 club property for omega 1. Okay, now for the other implications, so for the remaining three, we have the following theorem. So if we have some sigma 1 formula and some parameter from h omega 1, then if there is a stationary set such that the sigma 1 formula holds, then there's actually an element of the club filter where the sigma 1 statement holds. And the same for co-stationary and non-stationary. So the reason why we originally proved this is that we wanted to show that there is no, under these assumptions, there's no delta 1 definable set that separates the club filter from the non-stationary ideal. Yeah, so because if there was such a set, then somewhere there's something in the middle between the club filter and the non-stationary ideal, so either stationary or co-stationary set, but then the separating set automatically contains either a club or a non-stationary set. And the proof of this theorem is really very close to the proof about well-orderings I showed you in the beginning, because what you can do, you again take these models that are generically iterable, and if you're stationary, you can throw your set into the generic filter, and make sure that the critical point of the generic embedding is in the image of the set. So if you do this in every step, you get this club of critical points, and they are all in the last image of the set you consider. And the last image of in the last model, the sigma 1 formula will hold. So you get this image of A in the last model, and it will satisfy the sigma 1 definition, but it contains the club of critical points. And the same with co-stationary, so you get all of the critical points are outside of this final image. Okay, but of course, if we do this with a singleton, we get either a club that's in the set or disjoint from the set, so you get the sigma 1 club property. Okay, so this is what I just said. Okay, and then we can do the same with large cardinals as parameters. Okay, so now we'll give a very explicit formulation of this lemma. Okay, so we take some sigma 1 statement with an element of h kappa as a parameter, and kappa is just some uncountable regular cardinal. And we assume that this sigma 1 formula and the parameter define a unique set A. Now, if all of these things are contained in some iterable model, then this uniquely defined set either contains a club or is disjoint from a club. And that's the same trick. So you take the model, you take a small submodel, you iterate it up again, and if the set was an element of the filter, then the club of critical points will be in the final image, and if it was the complement was in the filter, then this club will be disjoint from the last image of the set. Okay. Okay, and what this means is that both iterable cardinals and stationary limits of iterable cardinals have this sigma 1. Okay, so again we have that omega 1 and large cardinals are examples of cardinals with this sigma 1 club property, and now the question is what other kinds of cardinals can have this property. And we'll now show you a short argument that shows that cardinals with the sigma 1 club property are either equal to omega 1 or they are limit cardinals, and omega 1 is the only cardinal that can possess the sigma 2 club property. And this is exactly because if you have other cofinalities, then you can easily define stationary sets that are simply definable and bistationary. Okay, and this is just the proof. This will be the proof of this proposition. So if you have an uncountable cardinal, then the successor of this cardinal does not have the sigma 1 property, and regular cardinals greater than omega 1 do not have the sigma 2 club property. Okay, and I think I have a lengthy proof of this, but it's actually quite simple. So first of all, let's show that successors of regular cardinals do not have this sigma 1 club property. So if you have some limit ordinal smaller than the successor, then the assumption that there's a strictly increasing cofinal function from the cardinal to this ordinal, this implies that the cofinality is mu. And in the other case, if there's a smaller limit ordinal and a cofinal function, then the cofinality is smaller than mu. But now this is a sigma 1 definition of S mu plus mu. Okay, so this shows that successors of regular cardinals do not have the sigma 1 club property.
I mean, since you have this somehow counterexample, you could restrict it to this.
Yeah.
And then.
Yeah, of course. There's something you can show something there for restricted parameter sets. We have some results, but I will not talk about this. I mean, there are actually interesting cases, for example, for successors of singulars, but I will just consider the boldface property here. Okay, so now for arbitrary successors of uncountable cardinals, let's assume that such a cardinal has the sigma 1 club property. So then it has to be a successor of a singular cardinal by the first argument. And now we can take the set of all smaller uncountable regular cardinals as a parameter. And then we get a sigma 1 definition of S nu plus omega, just using this parameter Z. Okay, so no successor cardinals above omega 1 have this omega 1, have the sigma 1 club property. Okay, and for the final statement that omega 1 is the only cardinal that can possibly have the sigma 2 club property. Okay, there are, this should be the singleton of S kappa omega, but this is easy to see that this is sigma 2 definable just from kappa. Okay, so this restricts the possibilities, but it actually turns out that all other constellations are possible. So, so if you have an inaccessible cardinal with a sigma 1 club property, then we can either add that many cone subsets, or we can collapse it to become omega 1. And in the generic extension, the cardinal will still have the sigma 1 club property. And what's really important here is that the singletons of these four things, they are sigma 1 definable because the conditions are finite. And it's actually false if you replace omega by omega 1 there. I mean, this is the reason why you cannot use this to get the sigma 1 club property at omega 2, because the corresponding Levi collapse is not sigma 1 definable. But here you can just say, okay, I take the Levi collapse from L, and it's the same as a Levi collapse in V, and that's sigma 1 definable. The singleton of this is sigma 1 definable. Okay, and then it's just some computation where you check the complexity of forcing statements, but you stay within the class of sigma 1 statements when you look at the forcing. And the proof shows that if you had a counterexample for the sigma 1 club property in the generic extension, then the corresponding forcing statement would give you a counterexample in the ground model. Okay, and then a slightly more complicated argument shows that then you can turn this cardinal into omega 1, and in the generic extension, no bistationary subset of omega 1 is contained in hot of R. So in particular, omega 1 will have the sigma 2 club property there. I mean, the forcing is a bit more complicated, but it's actually rather well known because this is just the forcing, or a simpler version of the forcing that makes a non-stationary ideal on omega 1 precipitous. But instead of iterated club shooting, you just shoot a club through every element of the filter here. So you collapse and then you shoot clubs. And you do it with a countable product and countable support product. And then you get this conclusion. So this is really just an easier version of this consistency result that the non-stationary ideal can be precipitous. And you use the fact that the forcings are homogeneous, so to talk about definability. Okay, so these are upper bounds for the consistency strength of these club properties. So, and this in particular tells us that the sigma 1 club property, it can hold at omega 1, it can hold at weakly inaccessibles that are not strongly inaccessible, and it can hold at strongly inaccessibles. And the sigma 2 club property, it can hold at omega 1, and that's the only possibility there. Okay, so now the last thing I want to do is present some results that tell us that the consistency strengths given by these forcing constructions are actually the correct ones. And for the sigma 2 club property, this is actually easy. So if omega 1 has a sigma 2 club property, then omega 1 is measurable in hot. And this is just because you take the club filter, you intersect it with hot. This is an element of hot, and it's an ultrafilter there. And actually, you can, I haven't defined it, but you can write light phase sigma 2, so you don't need the parameters from H kappa there, it's just kappa. And the other one is a bit more complicated, but this tells us that all of these sigma 1 club properties at the different cardinals, they are all equiconsistent with the existence of an inaccessible sigma 1, an inaccessible cardinal with a sigma 1 club property. And the result says that the sigma 1 club property is downwards absolute to the Dodge-Jensen core model, and there it implies inaccessibility. And actually recently Philip Welch, oh, there's a typo there, but he gave a better characterization of this property in the Dodge-Jensen core model. So he developed a notion of omega 1 stably measurable cardinals, and these are, in the Dodge-Jensen core model, these are exactly the inaccessible cardinals with the sigma 1 club property. And
What is this notion?
it's I don't want to write down the definition. I can show you later on. Yeah, but somehow it gives a better picture of what's going on than just saying inaccessible plus club property. Okay, so I want to show you how to prove this, and what I need is a notion of a good set of indiscernibles for some A subset of uncountable regular cardinal kappa, and this is just a subset of kappa with the following properties. So whenever I cut off the L kappa of A at some element of the set I, then I get an elementary substructure, and these sets are indiscernible for the structure where you also add the smaller indiscernibles as parameters. And it's not too hard to see that if you have the sigma n club property and you have a sigma n definable singleton, then you get a good set of indiscernibles for this subset. And this is just the coloring that checks the truth of first order statements. It's the same argument that shows you how to get indiscernibles from Ramsey cardinals. But the coloring is just simply definable because you look at L of A. But this now already gives us a lower bound for the sigma 1 club property, because if you have such indiscernibles, you get sharps. So sharps are a lower bound, and omega 1 iteral cardinals are an upper bound, and you're in this corridor. Okay, and another ingredient that we need is that if we have this club property and we have a singleton that's definable in this way, so sigma n formula with parameters in H kappa and also kappa as a parameter, then this cardinal is inaccessible in the corresponding L of A. And this actually requires some work. But what you do is you go through the proof why weakly compact cardinals are inaccessible, and you check whether if you're in this definable setting, then the counterexamples will also be definable, and you get a definable coloring without a large homogeneous set. But the sigma n club property already gives you a club homogeneous set. Okay, but this requires some work. And once you have inaccessible, you can get Marlow there, because there's a result of Todorcevich that says if you're inaccessible, then you are Marlow if and only if there are no special Ahrenstein trees. So, but the first special Ahrenstein tree in L of A is sigma 1 definable, if A is sigma 1 definable. So you can define this tree, but then the bad coloring you get from the tree is also sigma 1 definable. But since it's, so you have this rangle-like property in V, so you get a large homogeneous set, so you get a branch to the tree, but the tree was special. So you actually collapse the cardinal in V, so there's no such special tree. Okay, but we just need inaccessibility here. Okay, so now, so this is a lemma that has nothing to do with definability. I guess it's maybe due to Mitchell. So what does it say? So you have a subset of some kappa, and kappa is inaccessible in L of A. And then if there's a good set of indiscernibles for this A of size kappa, then you get some weak kappa model containing the subset and a countably complete filter for this model. So this is just some standard construction. And we can now combine these statements to see that if we have the sigma n club property and we have a sigma n singleton, then this subset will be contained in a weak kappa model, and we have a countably complete filter for this model. But then we can now use this to, so this is a fragment of Ramseyness, right? So a cardinal is a Ramsey cardinal if and only if you have such models for all subsets of kappa. So this the sigma n club property tells us that the cardinal is Ramsey with respect to sigma n definable singletons. And what's interesting is that in the Dodge-Jensen core model, this restricted Ramseyness actually characterizes the sigma 1 club property. So some cardinal has a sigma 1 club property if and only if for all sigma 1 definable singletons there are such iterable models. And the reason why we need this extra assumption that we are in the core model, or it suffices to assume that we have some good sigma 1 well ordering, is that in this lemma where we said, okay, this iterable models, they give us the clubs that are in the set or outside of the set. We needed the witness for the sigma 1 statement to be inside the model, so inside of this M. Yeah, so you have a sigma 1 statement that's true, but you want to define the witness for the sigma 1 statement in a sigma 1 way. And this is just possible if you have some definable well ordering. But in the core model, you can do it. You can define the first witness in the sigma 1 way. Okay, so now we can prove this theorem about the downwards absoluteness of the sigma 1 club property to the Dodge-Jensen core model. So let's take a subset of some cardinal kappa, and kappa now has a sigma 1 club property in V, and the subset, the singleton of the subset, is definable in the core model by some sigma 1 formula that uses the cardinal kappa and some parameter z of small cardinality as parameters. So now we already know that the sigma 1 club property implies the existence of sharps, so the core model is not L, so it's just the lower parts of iterable premise. So these are the very simple premise, right, for the Dodge-Jensen core model. And the class of all such iterable premise, this is sigma 1 definable. And this is basically because kappa is uncountable, so you can define iterability in a sigma 1 way. Okay, but this says that the core model itself is a sigma 1 kappa definable class. So this singleton will also be a sigma 1 singleton in V, because you can just take the definition from the core model and relativize it in V, and this will be a sigma 1 definition in V. Okay, but now we had this lemma that for sigma 1 definable singletons, we have good sets of indiscernibles. So we actually have a club of indiscernibles. So we get this club in V, But now there's a result of Jensen called the Jensen indiscernible lemma. And this now tells us that we can find a set of good indiscernibles of size kappa in the core model. Yeah, so if we have it in V, there's such a set in the core model. Okay, but now we use the next lemma that says that if we have this set of indiscernibles, then we can capture this set A in a weak kappa model that has a countably complete filter. But this filter will give us, so we get the conclusion that the set either contains a club or there's a club in the complement of the set, because it's contained in such an iterable model here. Okay, and then some variation of this result about inaccessibility also shows that cardinals with the sigma 1 club property, they have to be inaccessible in the core model. This is because this core model has a good sigma 1 well ordering. And whenever you have this, all cardinals with such partition properties, they have to be inaccessible. Okay, so this proves this downwards absoluteness. And this is already everything I wanted to tell you. There are just some more questions. I presented this observation that all large cardinals are compatible with a well ordering of the reals that's sigma 1 definable just using omega 2 as a parameter. But you might want to ask about well orderings of larger classes. So, for example, of H omega 3. So now you don't want to just well order the reals, but you also want to well order the subsets of omega 2. And I don't know how to do this. I mean, I can do this, but what I need is one additional parameter, namely a ladder system on omega 1. So a parameter of relative small cardinality, but I cannot do this just from omega 2. Okay, but this result I showed you earlier on about well ordering of the reals, this tells us that the statement is false if we reduce the numbers by 1. So no well ordering of H omega 2 is sigma 1 definable from omega 1. Okay, and then a question that is likely very hard. This observation about well orderings of the reals with parameter omega 2, the results of Aspero, they produce models where PFA has omega holds, but it's not clear if you can get something stronger there. So actually, very strong forcing axioms might rule out the existence of such a well ordering of the reals with sigma 1 with parameter omega 2. Okay, and then one final question that I already mentioned earlier on. So, as I said, it's easy to see if you have natural numbers m less than n, then singleton omega m is sigma 1 definable from omega n. But now, if you ask about if the smaller cardinals are, if they are sigma 1 definable from omega omega, and I actually have no clue. But what I can tell you is that if omega omega is row bottom, then there's no such definition. But this is because I tried to prove something, and then I realized that if this proof would work, I would show that omega omega can be row bottom. So, and the proof was too easy to show. So, yeah. So. I think this is an interesting question, and it's also might be something. I think it's still open whether PFA implies that omega omega is not row bottom. So it's possible that this is a consequence of PFA. that omega omega is not rho bottom. And if you could show that some forcing axiom implies that omega 1 is sigma 1 definable from omega omega, then you would prove that it's always not rho bottom.
So the first paragraph basically asks, can you do that in DFC? Or,
Yeah. So,
No, it's not known whether our
oh, no. Okay.
yeah, it's not.
That this is Aleph omega. Yeah, that's,
So it's not known whether this is consistent.
yes.
Okay, and this is all I wanted to say.
So if you just drop choice entirely, what can you say about, so I guess omega 1 is measurable in your AD, right?
Yeah.
So then you have all the, I mean, that.
At least these two properties
Right.
should just fail there.
Then you can ask what's consistent with larger cardinals. I guess omega 2 is also measurable. In LR.
Yeah.
Hard to get it's good. But then you're back into the
But once the club filter is ultra, then you have the ranges.
Yeah, for sigma 1.
Club homogeneous sets.
Yeah.
Okay. But then if you go into, I mean, you mentioned that if you're in the smaller core models, you have actually a sigma 1 well ordered with omega 1 as parameter. Right? Iterability condition is weak enough.
Yeah.
So I wonder what happens with the larger core models. They were internally,
Um,
when you start losing that property.
Yeah, so somehow, at some point, I mean, as soon as you have a wooden cardinal below a measurable cardinal, then this is somehow no longer a large cardinal property because you also have it for omega 1. So something happens somewhere between measurable and its strong assumption. But yeah, I don't really know what's going on there. And it might be difficult.
I remember when I was looking at the forcing well orders, there was something hard about, forcing a well order of H aleph omega plus 1. And the successor of the singular. Do you know how to do that?
With
I remember Oscar Rowe and I were doing things where we were using various guessing principles and forcing well orders.
Yeah. So, but you allow subsets of the cardinal as parameters, or just boldface?
And it's okay, the success.
I think so. At least if you in GCA over GCH models, I think it's okay. Because I think just making some well order of the ground model definable in sigma 1 way, just in the boldface sigma 1 way.
Yeah.
That's not really relevant if you're a successor of a singular cardinal or not.
Okay.
I think the problem is really if you just want to use bounded subsets as parameters. But I think for the boldface definition, you can just do some coding of something of the ground model into, say, the branches of a tree, and then the generic is also a subset of the cardinal, and you can define the ground model and well order it. I think that's not problematic. I think it gets problematic once you have failures of GCH, and you only want to use bounded subsets as parameters. I think then I don't know how to do it.
There's a very old result. I don't know if it's direct relevance. This is long before this stuff was Shalom Abraham, was it? The forcing well orders of the reals, which are third order.
Yeah. Yeah.
That was interesting. I don't know whether that was CH or not. Probably with. Yeah. right. Delta 2, 2. Interesting trick. I don't remember whether CH was holding or not.
Yeah, I'm also not sure.
All right, thank you, Philip.